Category O, Lecture 8, Parabolic Category O. So we work with a semi-simple finite-dimensional complexly algebra G with a fixed triangular decomposition into the negative part and minus, the Cartan subalgebra H, and the positive part and plus. Associated to this decomposition, we have the decomposition of the root system phi of G into negative and positive roots. And we denote by pi the basis of phi, which corresponds to this decomposition. The Borel subalgebra of G is the subalgebra defined as a sum of the Cartan subalgebra and the positive part. So definition: a parabolic subalgebra of G is a Lie subalgebra P of G which contains the Borel subalgebra B. For example, if we fix a subset sigma in our basis pi and consider the root system phi sigma, which is the root subsystem of phi generated by sigma, with the induced decomposition into the positive and negative roots. So phi sigma is the union of phi plus sigma, the positive part, and the phi minus sigma, the negative part. Then, associated to this set sigma, we have the parabolic subalgebra P sigma of G, defined as a sum of the Borel subalgebra B, with the direct sum of all negative root subspaces G alpha, where alpha runs through the negative part phi minus sigma. It is very easy to check that such pi sigma is a Lie subalgebra of G, and by definition it contains the Borel subalgebra B. So this is a parabolic subalgebra of G containing B. All parabolic subalgebras of G containing B can be classified, and the claim is that any parabolic subalgebra of G which contains B is of the form P sigma for some subset sigma of the set pi of all simple roots. To explain this, let P be a parabolic subalgebra of G containing the Borel subalgebra B. Then, of course, P by definition contains the Cartan subalgebra H, and hence is stable under the adjoint action of H. Therefore, P must inherit from G a root space decomposition. So if we assume that P contains some G alpha, where alpha is a negative root, then, commuting G alpha with the positive part and plus, we can obtain all root subspaces G minus beta, where beta is a simple root, so a root in pi, which appears in the decomposition of alpha with a non-zero coefficient. This implies that P must contain all negative root subspaces corresponding to simple roots, which appear in the decomposition of some negative root appearing in P. So this implies that P must be equal to P sigma. So for example, in the case of the Lie algebra SL3, we have exactly 4 parabolic subalgebras containing the standard Borel subalgebra consisting of all upper triangular matrices. So this is the Borel subalgebra, and it is also a parabolic subalgebra corresponding to the case when sigma is the empty set. Then, if sigma consists of one root, we have this parabolic subalgebra and this parabolic subalgebra. So the corresponding negative root subspace is this one or this one. And when sigma coincides with pi, so this means that our parabolic subalgebra should contain all negative versions of simple roots, then the corresponding parabolic subalgebra coincides with our Lie algebra. So SL3 has exactly 4 parabolic subalgebras containing the standard Borel subalgebra. Let us now define the parabolic category O. So recall that the usual category O is defined as the category of all finitely generated G modules, which are semi-simple with respect to the action of H and locally finite with respect to the action of U of n plus. Let us now fix a parabolic subalgebra P of G, which contains our Borel subalgebra B. The parabolic category OP, which corresponds to this parabolic subalgebra P is defined as a full subcategory of O, which consists of all modules in O, the action of the universe enveloping algebra of our parabolic subalgebra P, on which is locally finite. So we have two extreme examples. If the parabolic subalgebra P is equal to the Borel subalgebra, then the corresponding parabolic category O is just the usual category O, because the condition is just that this is a full subcategory of O consisting of all modules on which U of B is locally finite. So this coincides with O. The other extreme example, if we take as a parabolic subalgebra P the whole algebra G, this is the other extreme case, then the corresponding parabolic subcategory OP coincides with the category of all finite dimensional G modules. The parabolic category O was defined in the PhD thesis of Elvani Rocha-Caridi, which was published in the Transactions of the American Mathematical Society in 1980. So here is a reference to this paper. A parabolic category O is a Serre subcategory of O. Let's recall the definition of the Serre subcategory. A full subcategory S of an abelian category A is called a Serre subcategory, provided that for any short exact sequence M is a submodule of N with quotient K in the category A, the following condition is satisfied: the middle term N belongs to our subcategory if and only if the terms M and K belong to this subcategory. And the claim is that the parabolic category OP is a Serre subcategory of O. This follows directly from the fact that for any short exact sequence in O, so M is a submodule of N with quotient K in O, the action of UP on the middle term is locally finite if and only if this action is locally finite both on the first term M and the quotient term K. So the parabolic category O is indeed a Serre subcategory in O. Let us also recall that every object in O has finite lengths. So using this description of the Serre subcategory, it follows that the parabolic category OP is uniquely determined as a Serre subcategory of O by the simple objects which belong to this parabolic category. And we claim that if we assume that our parabolic category P is of the form P sigma for some subset sigma of simple roots, then for a weight lambda, so an element in the dual space to the Cartan, the corresponding simple highest weight module L lambda belongs to the parabolic category OP if and only if the evaluation of lambda at H alpha is a non-negative integer for any simple root alpha in sigma. To see this, we first note that in case the evaluation of lambda at some such H alpha is not a non-negative integer, then the element F alpha does not act locally finitely on L lambda. We have seen this in the previous lectures. But this is an element of our parabolic subalgebra, so which immediately tells us that such L lambda cannot be in the parabolic category. On the other hand, if this condition is satisfied, if the evaluation of lambda at each H alpha, where alpha is an element in sigma, is a non-negative integer, then the support, we have seen this also in the previous lectures, that the support of the corresponding highest weight module L lambda is locally finite in the direction of phi plus union with the negative part of phi sigma. Since all weight spaces for all modules in O are finite dimensional, it follows that the action of UP on such L lambda is locally finite. So this tells us that OP is a Serre subcategory of O, which is generated by all L lambda, such that the evaluation of lambda at H alpha is a non-negative integer for any simple root alpha, which defines our parabolic category P. So let's now discuss the block decomposition of OP. If we have a direct summand X of category O, then the intersection of X with OP is a direct summand of OP. So this follows immediately from the fact that OP is a Serre subcategory of O. So as soon as we take all simples in X which belong to P, the corresponding XP will be the Serre subcategory of X generated by those simples. A couple of warnings. First of all, there is no guarantee that this XP is not zero. It is perfectly possible that XP is a zero category. And another warning, there is no guarantee that if we start from an indecomposable block of O, that the corresponding XP, so the intersection of an indecomposable block of O with the parabolic category of P, that this is indecomposable. It might well decompose into a non-trivial direct sum of non-zero subcategories. But in any case, a consequence of this, that the central character decomposition of O, so O is isomorphic to a direct sum of O chi, where chi runs through the set of all central characters, induces a decomposition of OP into a direct sum of OP chi's, again where chi runs through the set of all central characters. Note that some of these OP chi's can be zero, and we know that already O chi's are usually decomposable, so the corresponding OP chi's are also usually decomposable, even if they are non-zero. So let's now discuss the parabolic induction. Denoted by L, or L sub P, the semisimple Lie subalgebra of G, generated by all elements F alpha, H alpha, and E alpha, where alpha is an element of our set sigma. So recall that sigma is the set of simple roots which defines our parabolic subalgebra P. So denoted by NP plus or minus the direct sum of all G alpha, where alpha is a positive, respectively negative root in phi, but which is outside of the positive or respectively negative roots in phi sigma. And also denoted by HL, the intersection of the Cartan subalgebra H with this Lie subalgebra L. Finally, denoted by HL orthogonal, the orthogonal complement to HL in H with respect to the Killing form. So we recall that the Killing form on H is non-degenerate, so for any subspace, in this case HL, we can define the corresponding orthogonal complement. So from these definitions, we have the decompositions that the whole algebra G decomposes into a direct sum of our parabolic subalgebra P and the negative part n minus P, and the parabolic subalgebra P itself decomposes into a direct sum of the semisimple part L, the abelian part HL orthogonal complement, and the nilpotent part n plus P. So n plus P is usually called the nilpotent radical of P. So given an L module V and a weight on HL orthogonal complement, so an element from the dual space to HL orthogonal complement, we can set that the positive part in P plus kills V, and that the elements from HL orthogonal complement act on V via scalars prescribed by the element nu. So in this way, we turn V into a P module. So when we now take this P module and induce from P to G, we will get a G module, and the process of starting from an L module and the weight nu and getting a G module defined in this way is usually called the parabolic induction. So we have a parabolic induction functor ind sub nu from L mod to G mod, which is defined in this way. So from the PBW theorem, it follows immediately that this is an exact functor. So we will use this functor to define parabolic Verma modules. So let us fix now a weight for the Cartan subalgebra, which has the property that its evaluation at all H alpha, where alpha is an element in sigma, is a non-negative integer. Denoted by mu, the restriction of lambda to HL, and by nu, the restriction of lambda to HL orthogonal complement. Consider the simple finite-dimensional L module V mu with highest weight mu. Note that this is well defined because the evaluation of mu at H alpha is by definition equal to the evaluation of lambda at H alpha for any alpha in sigma, and because of our assumptions, this is a non-negative integer. So this exactly implies that the highest weight module with this highest weight is finite dimensional for our semi-simple Lie algebra L. And the parabolic Verma module delta P lambda, which is associated to our weight lambda and our parabolic subalgebra P, is defined as the module parabolically induced from V mu using our weight nu, which was the restriction of lambda to HL orthogonal complement. So here our original weight lambda appears in the incarnation as mu and nu. So mu is a weight for L and nu is a weight for the orthogonal complement. Note that directly from the definition it follows that the parabolic Verma module delta P lambda is a highest weight module of highest weight lambda. In particular, it is a quotient of the Verma module delta of lambda. And of course, the simple highest weight module L lambda is a quotient of the parabolic Verma module. By construction, since at the last step of the parabolic induction, we have induction from P to G, the parabolic Verma module delta P lambda is free of finite rank, so this rank is a dimension of V mu, as a module over U of n minus P. So n minus P is exactly the difference between P and G. So the parabolic induction produces us a free Un minus P module, whose basis is the module V mu we start with. We can also give an alternative description of the parabolic Verma modules. For lambda as above, we have that for each simple root alpha in sigma, if we consider the Verma module delta as alpha dot lambda, it will be a submodule in delta lambda. So this is because the evaluation of lambda at H alpha is a non-negative integer. This corresponds exactly to the situation where the Verma module delta S alpha dot lambda is a submodule of delta lambda. So we can now consider the submodule K of delta lambda, which is given by summing all these Verma submodules delta S alpha dot lambda, where alpha runs through the whole set sigma. And we claim that the parabolic Verma module delta P lambda is the quotient of delta lambda modulo this submodule K. To prove this, let's first observe that by construction, the top of the submodule K is given by the simple highest weight modules L as alpha dot lambda, where alpha runs through sigma. On each such submodule, the corresponding element F alpha acts injectively, so in particular not locally finitely. So this means that K must belong to the kernel of the canonical projection from delta lambda to delta P lambda, because the elements in the top of K, they don't belong to OP, so they should die under this canonical projection. At the same time, let us, as before, denote by mu the restriction of lambda to HL, and by nu the restriction of lambda to the orthogonal complement of HL. So if we now consider the new part of our quotient delta lambda modulo K, so this is the set of all elements V in delta lambda modulo K, on which elements from HL orthogonal complement act via the scalars prescribed by nu, then we have that this new part of delta lambda modulo K is equal to V sub mu. And now, using the universal property of parabolic Verma modules, we can get that delta P of lambda surjects onto the quotient delta lambda modulo K. Let's consider an SL3 example. So consider the principal block of category O for SL3. So in the case of SL3, the Weil group is just the symmetric group S3, which consists of 6 elements, the element E, then the simple reflections S and T, and then the other elements are ST, TS, and W0, which is STS or TST. The highest weights of the simple modules in O0 are given by the orbit of 0 with respect to the dot action of W. So these are elements 0, so this is the trivial element times 0, minus alpha, which is S dot 0, minus beta, T dot 0, minus alpha minus 2 beta, this is TS dot 0, minus 2 alpha minus beta, this is ST dot 0, and minus 2 alpha minus 2 beta, which is W0 dot 0. And we have already seen that the Lewis structure of the dominant Verma module delta E is as follows, that we have LE on top, LW0 as the socle, and then in the rest we have LS, LT, LST, and LTS, and the submodule structure just gives us the Hasse diagram of the Brugha order on S3. Let us consider the parabolic subalgebra P given by the simple root corresponding to S. From our description before, it means that the simple modules from the principal block, which belong to the parabolic category OP, are the simple highest weight modules LE, LT, and LTS. So these are the modules whose weights are dominant with respect to the semisimple part of P. The semisimple part of P corresponds to the simple reflection S. So these are the dominant weights for S. And the Lewis structure of the parabolic Verma modules is as follows. So to understand this structure, we need to consider our picture for delta E. So in order to get delta E P, we should take delta E and factor out the submodule which is given by delta S dot P, which has top LS. So if from this delta we factor out the submodule generated by LS, this kills these 4 elements, and the quotient is given by top LE and socle LT. So the second parabolic Verma module corresponds to delta T. So we take delta T, this is this module, and we should kill the submodule given by delta ST. So this kills these 2 elements, and the outcome is the module with top LT and socle LTS. And finally, the third parabolic Verma module is delta TS. So we take the Verma module delta TS and factor out the submodule given by delta W0. The outcome is just one simple module LTS. So this gives us the structure of parabolic Verma modules for this particular example. Here are some warnings. So first of all, the general properties of parabolic Verma modules are not as nice as the general properties for the usual Verma modules. For example, we know that all Verma modules have simple socle. This is not true in general for parabolic Verma modules. There exist parabolic Verma modules which do not have simple socle. Further, we know that every morphism between Verma modules is either 0 or injective. This is not true in general for parabolic Verma modules, which we can already see in this slide. So there is a morphism from delta TP to delta EP, which sends the top LT here to the socle LT here. So this morphism kills LTS, so it's not injective. So not all morphisms between parabolic Verma modules are injective. And also the dimension of the homomorphism space between parabolic Verma modules might be bigger than 1. For Verma modules, it's at most 1. So homes between parabolic Verma modules are not as nice as between usual Verma modules. So using the BGG resolution of simple finite dimensional modules, one can construct a resolution of parabolic Verma modules in terms of Verma modules. So let WP be the parabolic subgroup of W generated by all simple reflections which corresponds to simple root in sigma. Sigma is our set of simple roots which defines our parabolic subalgebra P. Fix a weight lambda such that its evaluation at all H alpha, where alpha is a root in sigma, is a non-negative integer. For any non-negative integer I, denoted by mi, the direct sum of all Verma modules delta w dot lambda, where w is an element from the parabolic subgroup WP, which has lengths I. The claim: there is an exact sequence which starts from our parabolic Verma module delta p lambda, and then we have m0 surjects onto delta p lambda, then m1 goes to m0, m2 goes to m1, and so on. So we can resolve the parabolic Verma module delta p lambda by direct sums of Verma modules of this form. And in order to obtain this sequence, we can take the BGG resolution of the simple highest weight module V mu. So this is a simple highest weight module over the semi-simple subalgebra L inside G, which corresponds to the semi-simple part of our parabolic subalgebra P. So we take the BGG resolution of V mu over this algebra L, and then we apply our parabolic induction int nu to this BGG resolution. And this gives us exactly the resolution in the formulation of this proposition. In the very specific case, which we already saw an example in our SL3 example, when the simple highest weight module L lambda can be realized as the parabolic Verma module delta p of lambda, in our SL3 example, we are talking now about the simple highest weight module LTS. It can be realized as a parabolic Verma module delta TSP. So in case when we can realize our simple highest weight module as a parabolic Verma module, this proposition gives us an analog of the BGG resolution of the simple highest weight module in terms of Verma modules. And note that in this case, L lambda can now be infinite dimensional. So the bottom line is that some even infinite dimensional simple highest weight modules have an analog of the BGG resolution in terms of Verma modules for them. But the problem is that not every simple highest weight module can be realized as a parabolic Verma module for some parabolic subalgebra. In the SL3 example, we can realize LTS, we can realize LST by symmetry, but the modules LS and LT, they cannot be realized as simple parabolic Verma modules for some parabolic subalgebra. We have 4 parabolic subalgebras, so we can realize at most 4 modules. And these are LE, LST, LTS, and LW0. But in any case, we have more examples of BGG resolutions. Now let us talk about the Zuckerman functor. We want to construct projective and injective modules in O, and for this we need some functors. So we start with an exact inclusion IP from OP to O, which is given by definition of the category OP. Since this functor is exact, it has both a left and a right adjoint. Let's denote the left adjoint of it by ZP. So this functor ZP from O to the parabolic category is called the Zuckerman functor. And as a usual functor given by the left adjoint to an inclusion, this functor is given by starting from a module in O and taking the maximal possible quotient of that module, which belongs to the parabolic category. So in particular, we already saw that parabolic Verma modules are given by applying this Zuckerman functor to the usual Verma modules, at least under the assumption where lambda is a weight such that the corresponding L lambda is an object of the parabolic categories. This means that the evaluation of lambda at each h alpha is a non-negative integer, where alpha is a simple root belonging to sigma. Of course, we can also consider the right adjoint zp hat of our inclusion I pi. So this is again the functor from O to OP, which is usually called the dual Zuckerman functor. And being the right adjoint now, this functor is defined by taking the maximal submodule of a given module in O, which belongs to the parabolic category OP. So now using these functors, we can consider projective and injective modules in OP. So let's, for simplicity, denote by HP star the set of all weights lambda in H star such that the evaluation of lambda at h alpha is a non-negative integer for any alpha in sigma. This is exactly the set of all weights for which the corresponding simple highest weight module belongs to OP. So for lambda in H, L lambda belongs to OP if and only if lambda in HP star. Now we claim that the parabolic category OP has enough projectives. Moreover, we can be very concrete and say that for an element lambda in HP star, the corresponding projective module PP of lambda in OP is equal to the image under the Zuckerman functor ZP of the indecomposable projective module P lambda in category O. And the proof is as follows. So we have defined the Zuckerman functor ZP as the left adjoint of the inclusion functor IP. The inclusion functor is exact, and if you have a functor which is left adjoint to an exact functor, such a functor must send projective objects to projective objects. And since this functor is defined in terms of taking a quotient of the module, it must send modules with simple tops to modules with simple tops or zero. So in particular, it sends indecomposable projective objects to indecomposable projective objects or zero. And if we have a lambda in HP star, the claim is that the image of the corresponding indecomposable projective P lambda in O under ZP is non-zero, because we can compute the home space in OP from this image to L lambda using adjunction, so we move ZP to the right-hand side. So this home is equal to home in O from P lambda to the inclusion of L lambda in O, and this is non-zero. So this home is non-zero, which in particular means that the first argument of the home must be non-zero. So this implies that ZP of P lambda is exactly the indecomposable projective PP lambda. And dually, of course, the indecomposables injective in OP are IP lambda, which are the images under the dual Zuckerman functor of the indecomposable injectives I lambda, for each lambda an element from HP star. So category OP has enough projective and injective objects. So now let's talk about the duality and orthogonality in the category OP. First, we claim that the duality on O, category O, has a simple preserving duality, and the claim is that this duality restricts to a simple preserving duality on OP. OP is a Serre subcategory, and the duality is simple preserving and exact. So this claim is clear. Now let us define the dual parabolic Verma modules as duals of the parabolic Verma modules for each lambda an element in HP star. And again, similarly to category O, the claim is that the parabolic Verma modules and the parabolic dual Verma modules form two X-orthogonal families of modules. So the dimension of Xi from delta P lambda to nabla P mu in the parabolic category OP is equal to the Kronecker delta I0 and the Kronecker delta of lambda mu. So this is one-dimensional only if we talk about home and if lambda is equal to mu. In all other cases, this is zero-dimensional. And the proof is exactly the same as for category O, since we already mentioned that the parabolic Verma modules are free of finite rank over the universal enveloping algebra of the negative parabolic part n minus p. So similarly to category O, we can define f delta p as a full subcategory of OP consisting of all objects with parabolic Verma flag, and f nabla p dually as a full subcategory of OP consisting of all objects with dual parabolic Verma flag. So this slowly leads us to the BGG reciprocity for the parabolic category OP. This is a theorem from the original paper of Rocha-Caridi. Claim number 1, for any element lambda in HP star, the corresponding indecomposable projective object in the parabolic category has a parabolic Verma flag. Claim number 2, the multiplicity of a parabolic Verma module as a subquotient of a parabolic Verma flag of any decomposable projective in the parabolic category is well defined, which means it doesn't depend on the choice of the flag. And the claim number 3, the BGG reciprocity, if we take lambda and mu elements from HP star, then the multiplicity of delta P mu in PP lambda is equal to the composition multiplicity of L lambda in delta P mu. And again, the proof is basically the same as for the usual category O, because we have already established that parabolic Verma modules and dual parabolic Verma modules form X-orthogonal categories of modules. This is the fact which is behind the proof. And of course that we have a duality on the parabolic category. Using the duality, we in particular have as a corollary from the theorem that each indecomposable parabolic injective has a filtration by dual parabolic Verma modules, and the multiplicity of delta P mu in PP lambda is equal to the multiplicity of nabla P mu in I P lambda. The BGG reciprocity for parabolic category has some consequences. One consequence is that the parabolic category has finite global dimension. Again, this is similar to category O. Consequence number 2 is that each block of the parabolic category O is equivalent to the category of finite dimensional modules over some finite dimensional associative algebra. This is a consequence of the fact that the parabolic category has enough projective and injective objects. Corollary number 3, so if we have a module with parabolic Verma flag, then the multiplicity of each parabolic Verma in the parabolic Verma flag of this module M is well defined and can be computed as a dimension of the home from M to the dual parabolic Verma module, which corresponds to our original parabolic Verma module. And similarly, if we have a module with a dual parabolic Verma flag, then the multiplicity of each dual parabolic Verma in this module is well defined and can be computed as a dimension of the home of the corresponding parabolic Verma module to our module N. And all proofs of these consequences are similar to the corresponding proofs in category O. Let us finish with a couple of questions for PhD students. Question number 1. Formulate and prove the universal property for parabolic Verma modules, which is similar to that for the usual Verma modules, and which we actually used once in this lecture. Question number 2. Prove that parabolic Verma modules have only scalar endomorphisms. Question number 3. Construct analogs of the BGG resolution for all simple highest weight SL3 modules. Question number 4. Prove that the parabolic induction functor int nu sends Verma modules to Verma modules. And finally, question number 5. Prove that there is an isomorphism of functors from category O to category OP as follows. The Zuckerman functor ZP is isomorphic as a functor to the composition of the usual duality on O, followed by the dual Zuckerman functor Z hat P, followed by once again application of the restriction of the usual duality on O to OP. Thank you very much and see you next time.